Welcome to this presentation. My name is Mark Scythian. The date today is December 10, 2025. This presentation is a continuation of the previous presentation focusing on the AC city grid, electrical grid layout for 1041 homes. So in the previous presentation, we can see that the circuit then terminates to a power main circuit from the residential power distribution network. So this is now a low tension line having a constant voltage of 120 volts AC carrying 280,000 amps. But because the circuit is parallel, the voltage will remain constant, but only the current can drop into each home at 200 amps at a time. So we have a typical power factor of 0.875 to 0.88 on power mains to residential homes. We know the frequency is 60 cycles per second, 200 amp service, 120 volts AC, and that is an inductive circuit for which the current lags the voltage by a power factor of 0.875. And so that's also synonymous with the inverse cosine of the power factor to solve for the phase angle. So that's also saying current lagging the voltage by a phase angle of 28.36 degrees. So we have these preliminary specifications mapped out and understood. So now we have to design, build, and implement the power main circuit, which is usually at the utility pole or underground or perhaps on a peripheral power station delivery unit, depending on the city's politics. So we can start with the power main RLC circuit design calculations. We start by solving for the AC parallel impedance. So we can take the effective voltage divided into the total current. So 120 volts AC divided into 200 amps, so we get 0.6 ohms. Then we can quickly solve for the resistor value by simply dividing the parallel impedance into the power factor, so we get 0.7 ohms. And then we have to access the AC RLC parallel total current equation, which is a different setup compared to the AC series circuit equations for total current, because we're finding the reactive current in parallel. So that is the current at the resistor squared plus the difference between the current at the inductor subtracted from the current at the capacitor. This quantity then squared, then this sum is added up and its square root is found. This should then equal 200 amps. So I have to be a little careful here how we solve this. So we can start with the three equations for solving for current at the resistor, capacitor, and inductor for parallel RLC circuits because the voltage remains constant. So we'll only start with the first current at resistor equation. So that's just the effective voltage divided into the resistance, which we calculated up here. So we get 171.4 amps. Now we just take a break from these two, the current at the capacitor and the current at the inductor. We go back to our total current equation here, and we substitute the IC minus IL as X. So this will end up as X squared. So we put the known values into this total current equation. 200 amps is equal to the square root of the current at the resistor, 171.4 squared plus X quantity squared. So this becomes 200 is equal to the square root of 29,378 plus X squared. Then we square both sides to get rid of the square root. Then we get this value expression here, 40,000 is equal to 29,378 plus X squared. Then we continue on and we solve for X. And then we get its square root, the algebraic subtraction, until we get X squared is equal to 10,622. And so X is the square root of 10,622, 103.1. So because the current at the inductor must be greater than the current at the capacitor, we can use a 2-to-1 ratio. And so whatever capacitance and inductance values we calculate will match a heat rating. So we may have to adjust, instead of 50-50 split, maybe 40-60, maybe 45-55. But typically capacitors and inductors are already sold at a specific rating or value in conjunction with a heat rating. So it's not too terribly difficult to reassess the proportions, but initially we'll start with a 2-to-1 ratio. So this means the 103.1 we calculated for X can simply be doubled to equal the current at the inductor. So the current at the inductor is 206.2, and then the current at the capacitor is exactly 1/2 that value, 103.1. So we keep the inductive reactance equations, inductive reactance and capacitive reactance equations handy, because we can also solve for capacitive and inductive reactance by rearranging the current at capacitor and current at inductor equations. So we have the effective voltage divided into the current at capacitor for the capacitive reactance, and the effective voltage divided into the current at the inductor for inductive reactance. So we can quickly solve for the capacitive and inductive reactances by dividing these values out. So we get 1.16 ohms for the capacitive reactance and 0.58 ohms for the inductive reactance. So now we have all three values, and all we have left to do is to use the dedicated inductive and capacitive reactance equations to solve for the capacitance, C measured in farads, and then the inductance value measured in henries. So when we rearrange these two equations, we can solve for the inductance. So that's the inductive reactance divided into 2 pi f, or the angular frequency. So when we work this out, we have Henry's value for inductance of 0.001538, for which we convert to millihenries, 0.154. And the same thing for the capacitance. We take the 1 divided into 2 pi f times the capacitor reactance, rearranging this equation here. So we get this expression substituted, and then the following capacitance value of 0.002286709, for which we can change to the millifarads equivalent. So now we have all the information needed to build the circuit to facilitate the 200 amp service. So we can scroll down here and look at our design to fabrication manufacturing. So we have the AC RLC parallel power main circuit to house 200 amp service, and we've put the resistor, inductor, and capacitor in at 0.7 ohms for the resistor, 0.154 millihenries for the inductor, and 2.29 millifarads for the capacitor. So incoming from power main is 120 VAC, 208,270 amps, 60 cycles per second, power factor 0.88, current lagging the voltage. And then this circuit will tap only 200 amps out of this massive amount of amps to the house, and then it'll continue on down to the low tension lines in a ground circuit. And so after it passes through the circuit, it will go to the house with 120 VAC, 200 amps, 60 cycles per second. And then notice that if we recheck the power factor for correction, we can again install the impedance over the resistance and then see a slight variation to 0.86. So now it's all within spec. You're between 0.8 and 0.9 on average power factor to the home, and it's not typical or feasible to have a power factor of 1.0 just by the practicality. So the final check is to then enter in all these specs into the parallel impedance equation. So this is the dedicated equation to solve for AC parallel impedance. It's actually this equation. There's many derivations to solve for parallel impedance as well, but this is the dedicated long can version. So if we put in all these specs into the parallel impedance equation, we get indeed 0.6 ohms. So these values are correct. And again, we could go back up to the proportions here and adjust them accordingly to the heat rating. So perhaps when you purchase a capacitor, it is not exactly at 2.29. It might be at 2.3. You might have 0.15. So you can adjust slightly 1% up and down on that proportionality pretty simply to then calculate a change in the resistance, whatever you need. So you have the same mathematical outcomes, but slightly different specifications. So now the design engineering on the AC RLC parallel power main circuit is complete, and we've done all the checks. And so this is a good method. I would keep the inductive and capacitive reactances on note, and then the impedance on note, and then you can do the checks. So now we've completed the design engineering for the final phase of the city grid AC electrical layout. And so these units are usually contracted out with servicers that specialize in the design and manufacture. But then again, if our import policies change, we can use the same engineering methodology to then also start building our own power main circuits, as well as even our own transformers, which are much heavier duty, but they still obey the principles of AC circuit analysis and electrical engineering. Thank you for watching this presentation, and have a great day.